Hi everyone, this is Anurag. I'm a visiting instructor at Lander University where I teach a lot of data science courses like machine learning, data visualization, introduction to data science. Prior to that, I completed my master's at UNC Charlotte with a concentration in data science, where I worked as a teaching assistant for machine learning for about a year. Today, my topic is diffusion for images. We'll quickly go into what and why diffusion. Why should you learn diffusion in the first place? And then we'll talk about diffusion process. What is the training algorithm? What does the sampling algorithm look like? Sampling or inference look like? And we'll also code the training and sampling part of it at the very end. And then we'll also discuss the entire diffusion model architecture so that you can also go ahead and start to train it. So, before we get started, why should you learn diffusion in the first place, right? Currently, if you've already looked into what AI and all that is, you might have learned about ChatGPT and Grok. These are text large language models, which are heavily being used these days. The architecture that these models use is called as a transformer architecture. Uh, so, as an alternate to transformer architecture, which was introduced way back in 2017, diffusion can be a good architecture to use. And this has been proven recently, about a week ago, from Google Diffusion, which was released in Google I/O 2025, which gave very quick results, especially for text. But diffusion as an architecture comes especially from image generation. You might have already seen a lot of AI image generated videos or images, right? Diffusion is one of the cutting edge architectures used in image generation. And these days, diffusion is currently being used to generate text as well, since it's very fast during inference, or when you try to generate text, it is faster than the transformers architecture. So it is a very good alternate to know about. Diffusion is also very good in generating high quality text, images, videos, and not just all of these three, which we already discussed, but also audio, right? That diffusion as an architecture can also be used as to generate audio. So that's the reason why you should learn diffusion, which is a generative architecture in the first place. So what exactly is diffusion? Diffusion as an architecture, simply explained, is the ability to form an image from pure noise to a purified image or clarified image completely. So if you take a look at this here, the very first image block that you see is completely pure Gaussian noise. And then as it progresses to the next iteration, you slightly see that some qualities of that woman is being portrayed. And then as you go on through the iterations, right, a much more clarified image is being formed. So diffusion as a process, what it does is basically reconstruct the noise. When you give a noise, it reconstructs into whatever image you want to generate. So as you can see, these are a few iterations that I've developed myself or trained myself. If you see here, given pure noise, these are run over 1,000 iterations, 15 iterations, I believe, and then stored during time steps. But if you can see at the very end, you slowly start to build the image which represents a two, right? From a noised version of two, it slowly starts to get more clarified. We'll look at how these models are trained and how these inferences generated. But as I said earlier, diffusion is simply a learned denoising process where you denoise an image to get the more clarified picture. You can also give a condition to this, that is, let's say if you wanted to generate a black sparrow, you can also give, along with this noise, you can also give a condition that says, I want to generate a black sparrow, and it will do that for you. As the iterations progress, you'll slowly start to see a sparrow build up and then a black sparrow build up at the very end of this generation. So that is can generate image based on text prompt, which is also called as a condition. So diffusion as a process consists of mainly two processes in general. The first one is forward diffusion process, and the second one is called as reverse diffusion process. We'll look at a GIF so that you understand this much more clearly. We'll first talk about forward diffusion process. So what exactly is forward diffusion process is the ability to add noise gradually, right? So first, what you have in the training sample is maybe you have an image that has a lot of clarity, right? If you see there is a house, there is a mountain, which is a clarified image. What you do in case of forward diffusion is you add Gaussian noise to that image, which was given to you during training, right? So let's look at what actually happens. Is you're given this clarified image, and immediately what you first do is randomly select a time step t, and you add noise related to that time step. So if your time step was, let's say, 1, you would add a lot less noise. But if your time step was, let's say, 10, which was randomly selected, you end up adding a lot of noise at the very end. So the image itself can scale depending randomly on whichever time step is selected. So what happens then is you have this image, the noise is being generated based on the time step t, and then what you do is you add both of these together, and then you now have a slightly noised image. Then what you do next is you take this noised image as the input to the next iteration, and then this image that was noised now becomes the input to the second iteration that will take place. And then you do the same thing again, where you generate a random time step t that will do here. And then you create the noise of that time step, whichever that is. And then you end up adding that noise to this image that is given to you here, which was the output of the previous iteration. And then you get a much more noised image. And then you do this multiple times where you generate the noise, you add it, you slowly end up getting completely noised image. If you see the image features are completely being depleted with entirely noise, right? So you slowly start to see that there is entirely noise being generated at the very end. So why do you do this? You do this because you want to feed this, you want the model to predict the noise that you've added. So let's assume you are given this clarified image at time step 0, and you randomly ask it to predict time step, which as let's assume it selected t. So what you do is you create this noised image from the time step 0. So this will be your output. So what you want your model to generate is the noise, to estimate the noise that you've added to this image. So what you do is you give it the noise that you've added, and you give it this image that you've generated uh, after adding the noise. And then what you want the model to estimate is how much noise did you actually add to the image, as simple as that. So your model output will be what is the amount of noise that I've added. And I'll tell you why we estimate the noise and not directly the image. But for now, what I want you to understand is the model itself is trained to generate noise that was added, to estimate the noise that was added to the clarified image, right? So that's the forward diffusion process. Now let's look at backward diffusion process. Backward diffusion process is where you slowly start to generate the clarified image, right? During inference, you want to generate a much more clarified image, right? You want a clarified image to show your users. So how does it work? Is you first start with a completely noised image, and this diffusion model is trained now. So, like I said, think about this for a second. What is the output of this diffusion model, right? So the diffusion model's output here is once again noise. So if you pass in this noised image to a diffusion model, it also generates noise. So why does it do this? Is because it generates something that you want to subtract from this original noise. So diffusion model as a process gives you some noise that you can subtract from this original image. So if you see, I'm subtracting this original image with the noise that diffusion model gave me using this formula here, and then you have this image as output. You'll once again do the same thing where this image that came as output is fed into the diffusion model again, and then you ask it to generate the noise that it can subtract from itself in order to form a much more clarified image, right? So now that you have this, you say feed it into the diffusion model, you ask it to generate some noise, and this noise is again subtracted from the original image. You go on to do this multiple times. What happens is it slowly starts to converge towards the image that we want. If you see, color started forming up right about here. So you slowly start to see that the pixels itself, each pixel has a decision to make towards which direction it should go. And that is decided by this diffusion model to predict what it should subtract from this current image so that it can form a much more clarified image. As simple as that. So xt here is the current image that we have, which is this, and e theta xtt is the denoised output, or sorry, whatever the predicted diffusion model predicted, that noise is given here. So you subtract this image that was the actual output minus whatever the diffusion model predicted. So you give xt minus e theta t, and you do that multiple times, and xt minus 1 is again fed into this network. And then you see you ask it to generate noise, you subtract that noise again from this, and you do this multiple times. And there is one more slightly important thing that here to discuss is, if you see this noise we are adding at the very end, this e theta, what is this? I mean, you understand this xt minus e theta t, which is the image minus the predicted noise, so that you're denoising this image multiple times through the iterations. But if you see, this is also a slightly noised, you're also adding noise at each step. This is because you don't exactly want to generate the same image in your training set, but maybe something slightly in neighborhood of the previous image, right? Given if your training set has a red sparrow, you don't again want to generate a red sparrow, right? You might want to generate a black sparrow, green sparrow. A green sparrow might not exist, but or maybe it does. But what you want to do is generate something in the neighborhood of that training image given to you, and that this noise that you're adding at each step is what it takes place. And this noise is not added the very last step, because you want the image to be of entirely good quality. So you don't add that noise here, but the noise that was added earlier was so that in the generation process itself, you don't generate the same image that was present in the training set. So revisiting this backward diffusion model process again, what you have is an image. You pass that to a diffusion model. You generate the predicted noise that this image can subtract from itself in order to generate a much more clarified image. And you do this for 10 iterations or 15 iterations or how many ever iterations you want. So this is called as reverse diffusion process. Forward diffusion process is where you took a clear image, you added noise, you add noise to it multiple times. And during denoising is when you take a noise example, and then you slowly start to generate a much more clarified version of it. So this is diffusion process. Let's look at these formulas directly. Do not get worried about all of these mathematical equations. If you understand this notations clearly, you're more than halfway there. It's very simple to understand, and we'll also look at these math here, exactly how you generate what are these alpha values in just a bit. But I want you to think about for a second, what does forward diffusion do and what does reverse diffusion do as a process. Forward diffusion adds noise, generates that image, and asks the model how much exactly how much exactly noise did I add? You have your original clarified image, you have your noise added image. You give this noise added image along with the actual noise, so predicted noise and actual noise, to the model, and then you ask it to predict this actual noise, which I can subtract from my given image, and I do that multiple times. So it's as simple as that. The model here is asked to generate noise, right? Which is slightly counterintuitive, but the model itself is asked to generate noise that can be subtracted from the original image multiple times so that you generate the image, a much more clarified image. So what exactly happens during training, right? During training, you firstly take a randomly sampled data point from our training set. And I want you to think about this for a second. What is a randomly sampled data point in your data set? Uh, for example, in this case, a training set could be something like an image, multiple images, right? Since we're talking about diffusion for images, a sampled data point, randomly sampled data point is just a regular image. It can be an image of whatever we are training on. We'll take a look at that data set just in just a second. So we'll look at that code now. If you see here, the dataset that we are today using is called as MNIST dataset. MNIST dataset, for those of you who don't know about this, is a 60,000 numeric dataset where each image consists of a number, right? Something like this, where earlier you had an image of 2. you have about 6,000 images of 2, you have 6,000 images of 1, 0, right? So you have 10 classes, each class is a number, and each image consists of a number, and about 6,000 images is for each digit. So that's MNIST dataset that we're using today. Data loader, what it does is it simply loads all of these images into a batch. Let's assume you have 32 images. Let's assume you have 6,000 images, right, in total for a single class of images of 0. What you then do is you load up each batch with 32 images. Next batch is 32 images. Next batch is 32 images. This is because you want to not process all the images at once, but rather take it batch by batch so that the processing itself is faster. So next comes training process here. Before we've looked into the data set now, let's look at DDPM scheduler, what this is. So DDPM scheduler, if you remember this forward training process, what you do is you select a random time step. Let's assume you have 1,000 time steps. You select a random time step of 555, and that 555 will tell you exactly how much noise to add. If you have an image with zero at zero time step, you'll add less noise. But if you add time step 100, you might add more noise. 500, more noise than the 100th one, and so on and so forth. So you select a random time step t, and this alpha value, basically that you see in this formula here, will scale that noise correctly so that you end up adding less noise or more noise depending on whichever random time step you take. And if you see alpha t here is given how much noise you want to add. This x0 is the original image that you have. Alpha 1 minus alpha t is just you adding more noise. This e itself is the direct randomly generated noise that you have. And so these are scaling factors to the noise itself that you see here in this formula. So these alpha values range from 0.0001 to 0.002. So as you can see, these are very minute values, but they end up adding a lot of noise even when you take these small values. 1 minus beta, that this is beta value, and 1 minus beta is alpha. And if you see, this cumulative product is just you adding, you multiplying all the values from the very beginning. So you'll have values. If you have an array of 1, 2, 3, you get 1, 2, 6 because 3 times 2 times 1, right? So you might end up multiplying it cumulatively from the very beginning. So that's that you see here. So now that you have DDPM scheduler, you talk about UNet. UNet is an architecture. Simply, you can say that if given an image of size 2 by 2, if you pass this to a UNet architecture, it generates 2 by 2 of the same size of the image passed, but it can be changed however you like it. It's a U-shaped CNN level architecture. If I had 15 more minutes, I would go into detail about this. But just know that for now, UNet is a U-shaped architecture which consists of convolution neural networks, which will generate the exactly same size of the image passed. Whatever characteristics you want to add, you'll have that in your training set. But it was originally trained to generate medically generated images. But for now, let's assume that now that we are at this point, what is the output of this model that we were talking about? The output here was the noise that we wanted to generate, which is exactly in the same shape as the image passed. So if you pass a 2 by 2 image, you expect a 2 by 2 noise, uh, to, uh, 2 by 2 noise that this model generates, which I'll take, subtract from this, generate a new image, pass this into a model again, and repeat this process all over. So unit here is a architecture or a model architecture that you want to train. Atom here that you see is an optimizer that updates gradients much faster. Gradients is where you update model weights so that they understand how much, what exactly the output you want to generate. They learn something, right? That's all this is. In order for the model to learn faster, is where you use is why you use this Atom optimizer. And all of this for now is just so that you sort of store. Let's assume you train a model for 1,000 iterations. You don't want to train it 1,000 iterations at a stretch. But what you want to do is maybe uh, for the first 500 iterations, you take the model, you save it someplace. And then at 750 iterations, you take the model, you save it someplace, right? So that you don't have, you would, even if it fails somewhere, you don't want to retrain it again from scratch. And this is called as a checkpoint, where you store these weights if that checkpoint is hit in between. You're loading these checkpoints here, and you end up saving these checkpoints here. But that's all these checkpoints are, is to store those weights, store those optimizer numbers correctly, so that you can just directly load it up whenever you want later on. So the criteria here is, or the loss function here that we see is regular MSE. MSE is nothing but actual value minus predicted value whole square. Okay, so you want to reward the model when it gets very close to the actual value, and you want to sort of say that if it's very far away from the uh, if the predicted value is far away from the actual value, you want to say that you want to maximize that difference and say that you're going wrong here, adjust it so that this distance is shorter. And that's all MSE loss clearly is when you think about it in terms of intuition. So we are simply loading those batches. If you remember, we've loaded uh, 10,000, let's assume 32 images in each batch. You're loading each batch now, or each image in that batch, and you're training it for number of epochs. Number of epochs, I believe, was 15. So you end up training each batch 15 times to the model. So you pick out a single image, and this is where we are currently at in terms of algorithm training. So you've taken a randomly sampled data point from our data set. Yes, we did. X here. We've changed this padding is just you adding 2 rows at the very end. So that end of that image, because image is just a bunch of pixel values, you end up adding that padding at the very end. You're just changing that here. So let's look at what is the next step. Select a random time step on our noise variance schedule. This is just a fancy way of saying select a random time step. And then based on that time step, you want to adjust the amount of noise you want to add, which was very exactly what we discussed earlier. So you have this t value that you have randomly selected between 0 and 1,000. Number of time steps is 1,000. E here is the noise that you see in this formula here. E here is the noise that you want to add, which is exactly in the shape of an image. So that's the reason we have rand n like x, where you want to generate the shape exactly with respect to uh, shape of x. And then you pick out scheduler.alpha t is simply picking out how much you want to add from that time step t. If you wanted to add more noise if you're at the 100th step, and if you wanted to add less noise if you're at the 50th step. So this is what it does. And then we are directly using this formula in order to generate that model noise. So if you see, you're passing that noise added image now and t in order to generate this output. And if you see, you're using output, the predicted value of the model, comma, the actual noise that you have, and you want the model, you're training the model to say, I want to generate noise, I want to generate noise, so that you generate noise that was added to the original image, so that you can subtract it and get your clarified image. So that is what we are trying to do here. Add the noise, pass that to an image, pass that to a model, ask it to generate noise, subtract it from our original image, and then go on to do this multiple times during our training. And this is the mathematical representation of it. Sampling is exactly what we looked at here, right? You pass that image into something, that noise is again handled with respect to this formula, and then you subtract that from an image. So if you see, that's exactly what we are trying to do. All of these are explanatory, like I explained earlier. Simply what you do is you pick out the time step t, you figure out the beta value or the alpha value which scales that noise, you subtract it from our original image, and that's going on here, where if you see model of z gives you that noise that you can subtract from the original image that you have. You do this multiple times, and at the very end, you don't add that noise value. So basically, it exactly uses this formula that we discussed. And the simple idea behind this is you're subtracting the original image minus the noise that was predicted by the model, and you do this for multiple iterations. So that's the sampling algorithm. I want you to go through this once again. Fun idea would be to code this up from scratch by yourself, see where you're going wrong, see where you're getting it right, so that you see that even though these math are very complicated, the fundamental idea behind this is very simple. So this is the architecture. Basically, it's exactly what we discussed. You train it, you pass it to unit, it predicts some noise. It subtract that noise from the original image. You create this image, right? You pass this image that you get into the next iteration as input. You do this multiple times, and then the noise itself is completely diminished, and you generate an image that is of high clarity. It might not be the same as what you have in training sample, but it's in the neighborhood of that training sample, whichever you have. And I've trained this code that you see here. I'll also send this code, but this is the output that will be where you see each image being generated from noise entirely. And coming to applications, you can use it for text generation, you can use it for image generation, you can use it for video generation. Audio synthesis is also an application here. And if you have any questions, feel free to send me an email at ekalaku@uncc.edu. I hope you've like this lecture. And if you have any questions, feel free to always reach out to me at this email. Thank you very much. Have a great day.